This video is about intermolecular forces and properties. By the end of this video, you should be able to explain why IMFs affect properties and be able to predict relative properties based on IMFs. Recall that intermolecular forces are forces of attraction between molecules. They affect many physical properties. Any property that relies on the attraction between the particles or the amount of energy required to separate the particles will be affected by intermolecular forces. As we saw in the previous video, properties like boiling point and melting point are the most common. In this video, we'll look at a few others. First, viscosity. Viscosity is a measure of a liquid's resistance to flow. As you can see in the picture here, the least viscous substances appear to be these two, since they flow quite easily, and the most viscous appear to be these two. Molecules with stronger intermolecular forces will be more viscous. Likewise, larger molecules also tend to be more viscous. Viscosity decreases with temperature, which should be consistent with your everyday experience. As things heat up, they tend to flow more easily. Here we see a number of hydrocarbons, each time we increase the number of carbons in our hydrocarbon chain. All of these molecules are nonpolar. However, they display dispersion forces. Notice that as the molecule gets larger and the electron cloud increases, the strength of those dispersion forces increases, causing the viscosity to increase. Capillary action is another property affected by IMFs. This is the ability of a liquid to flow in a narrow space in opposition to gravity. Liquids are often said to climb up a narrow tube. You also see this when you put a paper towel into a liquid, and the liquid literally looks like it's climbing up the paper towel. Molecules that are strongly attracted to one another will be able to pull each other up as they travel up the tube. The type of meniscus is also affected by IMFs. Polar liquids like water will exhibit a concave meniscus, as seen here. You see the small indent in the meniscus. This is because the adhesive forces, meaning the forces between the water molecules and the material of the glass, are stronger than the cohesive forces, the forces between the molecules. Nonpolar liquids, on the other hand, will form a convex meniscus. Here we see that with mercury. This curves up. Here, the cohesive forces between the mercury particles is greater than the adhesive forces between the mercury and the glass. Looking at this on the particle level, again, we see that the water is able to adhere to the glass and climb up the sides, whereas mercury is not able to adhere to the glass and therefore does not climb up the sides. Solubility is another important factor influenced by intermolecular forces. As you may know, we often use the term like dissolves like to remind us that polar solvents tend to dissolve polar solutes better than nonpolar solvents. Note, this is a generalization only, but it holds up for the most part. Ionic substances are polar, therefore they dissolve in polar solvents, but not in nonpolar solvents. Here's a list of common polar solvents and common nonpolar solvents. Another property affected by IMFs is deviation from ideal gas behavior. As we saw before, particles will deviate from ideal gas behavior at high pressures and low temperatures. Notice here that carbon dioxide exhibits the greatest deviation from ideal gas behavior. This is because carbon dioxide has the strongest intermolecular forces. It's the largest molecule, and all of the molecules exhibit dispersion forces. Therefore, the largest one will have the strongest. Next in line would be CH4, since it has the next strongest intermolecular forces. Recall that these gases deviate from ideal behavior because the attractions between particles begin to matter. So it should follow that for molecules with stronger intermolecular forces, these IMFs will start to matter sooner. Finally, phase changes are another property affected by IMFs. As we saw in the previous video, molecules with strong IMFs will have higher melting points and higher boiling points. This is because the particles are more strongly attracted to one another. Therefore, more kinetic energy is required to separate the particles from one another. These graphs you've seen before, but notice here we're looking at hydrides of different elements in the same group. Notice that the molecules that exhibit hydrogen bonding have much higher boiling points than those in the same group that do not exhibit hydrogen bonding. Stronger IMFs means more energy is required to separate the particles, and therefore the boiling point is higher. Likewise, here we have a series of molecules exhibiting dispersion forces. As the molecules get larger and have more and more electrons, the dispersion forces become stronger, causing the boiling point to become higher and higher. IMFs also affect the energy required to complete a phase change. Recall that the energy changes associated with change of state are referred to as the heat of fusion, the transition from solid to liquid, and heat of vaporization, the transition from liquid to gas. In both cases, recall that the temperature does not increase, since all of the energy is devoted to separating the particles to complete the phase change. If we compare the heat of fusion, the heat of vaporization, or the heat of sublimation between different molecules with different strengths of IMFs, we see a clear trend. Butane, which has the weakest intermolecular forces, only exhibiting dispersion forces, has the lowest for each of these values, whereas water and mercury, which have the strongest IMFs, exhibit the highest values for each of these. In each case, when molecules exhibit stronger IMFs, more energy is required to separate the molecules from one another. Therefore, more energy will be needed to complete the phase change. Notice here that mercury's values are much higher than that of water. This may be surprising, since mercury exhibits dispersion forces and water exhibits hydrogen bonding. However, given the very large number of electrons that an atom of mercury has, its dispersion forces are actually stronger than the hydrogen bonds of water. This can occur sometimes with very large molecules, so it's not enough to just assume that dispersion forces will be weaker than other forms of IMFs. Very strong dispersion forces can actually surpass other IMFs in terms of strength. That brings us to the end of this video. Let's review our goals. First, we explained why IMFs affect properties, and then we learned to predict relative properties based on IMFs.